Okay, so welcome everyone to the final One World talk of the academic year. So we're very happy to have Ekaterina Rapinchuk to give the final talk. So Ekaterina, she did her PhD at UCLA, where I think you won several awards for your thesis, including the Pacific Journal of Mathematics Dissertation Prize, and then you won a University of California President's Postdoctoral Fellowship. You are currently a tenure track assistant professor at Michigan State University. Yes, we're very happy to have you here to give the final talk of the academic year, and you'll be talking about a fast graph-based classification method with application to 3D sensory data in the form of point clouds. Thank you.
So thank you so much. First of all, I'll just thank the organizers for allowing me to give a talk today. It's my pleasure. So today I'll be talking about a fast graph-based data classification method with applications to 3D sensory data in form of 3D point clouds. And so part of this work is joint with Matt Jacobs and Selim Asidoglu. So the problem we'll be talking about today is very simple to understand. So it's basically just data classification or segmentation. So in other words, the goal is to segment a data set into some pre-specified number of clusters. So in this case, it will be denoted by M. Segment a data set into M clusters or classes using some small amount of labeled data. And for experiments, we usually use no more than 2.5% of the data set as labeled, so a very small amount of labels. Okay, so if we look at the data set in the picture, it's a data set of images of different animals, and if the data classification problem is applied to this data set, basically the goal would be to correctly label each image with the correct animal. So this classification and segmentation problem is very, very important. It occurs in many different applications, including internet fraud detection, face recognition, digits recognition, video tracking, and so on. So it's a very, very important problem to be able to do efficiently and accurately. However, unfortunately, this problem does come with some challenges. So one of the biggest challenges for the data classification problem is the fact that for many applications, labeled data is very, very scarce. And this is often due to the cost and time associated with labeling data. And in fact, for some applications, you need experts to label the data. So labeled data is very scarce. In addition, unfortunately, many methods do require quite large amounts of labeled data to perform well. And this obviously becomes a problem when there are few labeled elements, which occurs in quite a lot of the cases. But there's also a curious fact that unlike labeled data, unlabeled data is often easy to find, and you could also do it. You could also obtain unlabeled data in a quite cheap way. So unlabeled data is usually easy to find. Labeled data, on the other hand, is often scarce. But many methods require large amounts of labeled data. So the goal of today's talk is to introduce a forward and reverse auction method for data classification for data with limited labeled samples. So when you don't have a lot of labels or labeled elements. And this method, curiously, proceeds very similarly to a real-life auction. So in this method, the data elements will submit bids to a class of their choice or a class computed by a certain procedure. So just like what would happen in a real-life auction. To reduce the amount of labeled data needed, this algorithm uses semi-supervised similarity graph-based setting, and also it incorporates class size information. So in this semi-supervised setting, we embed the data into a graph, where the vast majority of the data embedded into a graph is unlabeled data, which, as I mentioned before, is often easy to find. We also use a graph-based setting, so we're going to embed everything into a similarity graph with weights. Okay, so our approach to the problem is the following. So we're going to link a data classification setting to solving a series of modified assignment problems, which we're going to solve by newly formulated forward and reverse auction dynamics. So before going into the details of the procedure, I'll just like to mention some of the advantages of the method. So I guess the main advantage of this procedure is that it does require less labeled data than a lot of competing methods to reach good accuracy. So for this method, you often don't need that much labeled data, which becomes extremely useful for the many applications where labeled data is scarce. Another good property of the method is that it is able to incorporate class size information. So for some data sets, you have some sort of an idea of how large the classes are. So you might not know the exact class size number, but you might know that it lies between some lower bound and some upper bound. So our procedure is able to incorporate class size information in form of upper and lower class size bounds. So you can set the lower bound and you can set the upper bound for each class. Now, of course, if you know the class size exactly, obviously you can make them to be the same. And if you don't have any class size information, which obviously sometimes occurs, you can just set the lower bound to 0 and then the upper bound to the total size of the data set. So, and the thing about incorporating class size information is that it often can lead to better accuracy. So you can increase your accuracy often by incorporating class size information. And this method is also unconditionally stable with respect to parameters. So no matter what the parameter choice is, the method will converge and will give you some sort of a partition of the data. So our procedure, as I mentioned before, uses a graph-based framework with weights. So we embed the data set into a similarity graph, where each vertex represents a data set element. And then some data set elements are connected by edges, and the edges have weights on them, which represent how similar the two elements are to each other. So if it's a large value, the elements are more similar. If it's a small value, then they're not as similar. And if the weight is 0 or if there's no edge, that means the elements are very different. And so here I'll just say a few words about how we compute the weight function, which is the key property or the key element of the graph. So for each element of the data, we need to assign a d-dimensional vector. So each element of the data set needs to be assigned a d-dimensional vector called a feature vector. So some data sets come with this feature vector, but some do not. So for example, if your data set is a set of images, you need to construct some d-dimensional vector that describes your data set element. And obviously this can be done in many different ways. For example, you can construct this vector using principal component analysis or some other method. So basically, we need to assign a d-dimensional vector to each data set element. And then we use those feature vectors to compute the weight function. So the weight function is constructed so that it assigns a big value to similar elements and a small value for dissimilar elements. And there are many different weight functions that are used, but one popular one is the Gaussian. So, for example, this kind of function where kx of y is the L2 norm of the difference of the feature vectors of x and y. And then you have also a scaling parameter. So this type of weight function is often used. So, this is the function that we will use. Okay, so our classification model is going to incorporate the label data that we have. Then we also incorporate class size information. So we're gonna input the lower bound and the upper bound for each class. And then we also will incorporate region homogeneity terms, which will measure how well certain data elements fit into particular classes. So as I just mentioned, so region homogeneity terms denoted by R sub I of X measure how well data elements fit into particular classes. And by using them, we can improve the accuracy compared to if we were just to use an edge-based, just purely an edge-based technique. So the goal is to formulate R sub I of X so that R sub I of X is small if X is likely to belong to class I and large otherwise. Now for our application, which is 3D point clouds, we're going to construct R sub I of X using a number of different things. So we're going to use a correlation matrix, point coordinates, normal vectors, and variation of normal vectors. So we're going to use a combination of things to construct this term. So before going further, I would like to go over some notation that we'll be using for our method. So this is an optimization-based technique. So we're going to be optimizing over the variable u, which is a variable going from the vertex set, which represents the data set elements, to the simplex. So I use a function going from the vertex set to the simplex, where basically it's an m-dimensional vector and they're m classes. So m classes, it's an m-dimensional vector where all entries add up to 1 and they're all between 0 and 1. So basically it's a probability distribution. And once we solve this optimization problem over u, the optimal u sub I of X will represent the probability that X belongs to the ith class. Now L sub X, which is a value, an integer value from 1 to m, will denote the label of any data element with known class. Basically L sub X will be the label of element X. And then E sub I is an m-dimensional vector, so it's an indicator vector with a 1 in the ith place and 0 in all the other places. And we'll also denote the unlabeled data by T sub S and the labeled data by T sub R. Okay, so we will start with considering this optimization problem. So we're optimizing this energy over the variable u. This energy consists of two types of terms. So the first term is a graph-based term. So it has the weights. So it's a regularization term. And this term is actually convexified graph cut. So it's called the graph heat content. And then you have the regularization term. Or sorry, another regularization term, you have the region homogeneity term. But then you also have some constraints. So you have the simplex constraint, so meaning that u sub I of X must add up to 1 when going from I equals 1 to m for all X. Then you have the constraint of the labeled data. And then you also have your class size information. So the fact that each class must be, the size of each class must be between some lower bound and some upper bound. And so then a lambda is just some parameter which is more than 0. And then R sub I of X are going to be the region homogeneity terms. So once we solve this optimization problem, we're going to obtain some optimal U. And then from that U, you can obtain the optimal partition of the data set using the following simple procedures. So basically, each row of U will be a probability distribution of a certain element over the different classes. So we just assign each element to the class corresponding to the largest value in its probability distribution. And that will give us the partition of the data, which is our goal. And as you can see, the energy is a combination of edge-based terms with the weight function, or with the weights, and then region-based terms. So it actually turns out that if we have a positive semi-definite weight matrix, which is just a matrix consisting of all the weights. So for a positive semi-definite weight matrix composed of weight function entries, our energy is a concave function of U. So because of this property, we can obtain a minimization procedure for our optimization problem in the previous slide by successively minimizing linearizations of this energy that we had in the previous slide. So here we're minimizing linearizations of the energy, but then you also have some constraints, right? You have the simplex constraint, you have the class size information constraint, and then you have the label data constraint. And then after each step, you can obtain a partition by assigning just each element to the class corresponding to the biggest value in its probability distribution. So the concave property ensures that the energy is going to be non-decreasing at each step. And each iteration will produce a partition of the data. So our approach is to connect solving each iteration of our scheme to tackling a modified version of the Simon problem. And we'll solve this modified version using forward and reverse auction dynamics. So let me just remind everyone what the Simon problem is. So the Simon problem is the following. Given two disjoint sets X and L of equal size, and also a value function, the Simon problem seeks to find a one-to-one matching of X and L such that the total value of the matching consisting of this function A is as large as possible. So here we have two sets of equal size, and then you have this value function from each element of the first set to each element of the second set. And basically you just want to minimize this total value of the matching. So if we use a different notation, so if we use a binary vector notation, so we're going to use a binary vector z, where z sub l of x is 1 if x and l are matched, and 0 otherwise, we can rewrite this assignment problem in the following manner, in the following notation. So where you have some equality constraints. And the curious fact is that if we relax the binary constraint on z, the solution of the problem will actually not change. So let me now precisely go over the link between our two problems. So we're going to link minimizing linearizations of the graph heat content plus constraints to just solving a series of modified assignment problems. So it turns out that each step of our scheme is equivalent to a modified assignment problem with inequality constraints. So here is our modified assignment problem, where instead of equality constraints, we have some inequality constraints. So we have some inequality constraints here. We have the simplex constraint, the label data constraint, and then we have our modified assignment problem, where we have some linear term in terms of u. So we have some linear function in terms of u. And the factors in front of you are actually coefficients of the assignment problem, so auction coefficients. And so the auction coefficient A sub I of x, and we'll denote the auction coefficients by A. So the auction coefficients A sub I of x will represent how much data element x wants to be a member of class I. So basically our goal is to solve each iteration of our scheme by a modified auction dynamics technique. And to do so, we will use a market mechanism, which has the following three elements. So as in a real life auction, so each class will have an evolving membership price. So it's important to know that the price will change depending on the iteration. So the price will change. So each class has an evolving membership price, which everyone that is a member of that class must pay. And each data element will choose a class to submit bids to according to a certain strategy, which I'll describe shortly. And one thing we can do to satisfy the class size constraints or class size information is to make the most popular classes more expensive. Now, in our procedure, we also equip each class with an incentive. So if a class is having trouble obtaining the lower bound amount of members, then they can offer incentives, so T sub I, to attract data elements to the class in order to satisfy the class size constraints or information. And so in general, our strategy will be the following, that all data elements will want to be members of classes offering the best value to them. And so to compute the class that offers the best value, basically you want to find the argument of the maximum of the following values. So you're going to maximize over I the following values. So A sub I of x minus P sub I plus T sub I. So the auction coefficient, which represents how much a data set element wants to be a member of the class, minus the price plus the incentive. So whichever class maximizes this value is the class to which the data elements would want to submit bids to. Now, so obviously what we can do is just assign each data element to the class offering the best value to them, right? So given a certain price and incentive vector. So given a certain price and incentive vector, what we can do is just assign each element to the class offering the best value to them. So the class that maximizes this value, so auction coefficient minus the price plus the incentive. Now, while we can do that, the problem is that the class size constraints will probably not be satisfied. And an interesting question is the following: does there exist an equilibrium price vector and an equilibrium incentive vector that gives a feasible matching, meaning that satisfies class size information? And the answer is yes, there does exist. There do exist those kind of equilibrium incentive and price vectors. And the next question is, how do we find that? And the answer is actually in the dual problem of this modified assignment problem. So here we have an interesting theorem. So it turns out that the equilibrium price vector and the equilibrium incentive vector that give a feasible matching with respect to class size information are actually the solutions of the dual of the modified assignment problem. So once we solve the dual of the assignment problem, it will give us the equilibrium price and incentive vector. So, and here we have an extra auxiliary variable in this dual problem. So it's an optimization problem with 3 variables. So solving this problem will give us the equilibrium price and incentive vector. So our auction dynamics will actually simultaneously compute approximations to the price and incentive vector and assign data elements to classes using these values. So overall, we propose to solve each step of our scheme using the newly formulated forward and reverse auction dynamics with a market mechanism. And each step of our scheme will consider a different assignment problem with different auction coefficients and will produce a partition of the data set into M classes. And as I mentioned before, our algorithm has a very interesting property in that it simulates a real life auction. So things that would happen in a real life auction. So overall, each step of the algorithm will either modify the prices and incentives of the classes, or will increase the number of data elements that are matched to a certain class. So our auction dynamics has two different parts. It has a forward auction and a reverse auction. So a forward auction is something that would happen in a real life auction where the data elements will bid on the classes. Now, as you will see later, it turns out that to satisfy the lower bounds of the class sizes, you actually need a second step, which is the reverse auction. So in this case, the classes that are deficient members, according to class size constraints, so basically those classes that don't have the lower bound amount of members, so these classes will compete for data elements by providing incentives to attract the necessary number of members or the lower bound amount of members. Okay, so here is the first part of the algorithm, which is the forward auction. So okay, so here's the first part of the scheme. Okay, so if unmatched, the data element X bids on a certain class offering the best value to them. And this class is computed using the procedure that I mentioned earlier. So basically, we are trying to maximize the following values. So maximizing the class that gives the biggest value. So auction coefficient minus the price plus the incentive. And so this data element X, if unmatched, will submit a bid to the class chosen by the aforementioned strategy, and it will submit a specific bid. So it will submit this specific bid to the class. And the important thing about this bid is that it has this epsilon parameter. And this epsilon parameter is a parameter that is there to ensure that the auction will not run into an infinite loop, that it will converge. Okay, so once this unmatched data element X submits a bid to a class computed by this optimization strategy, it will submit a particular bid to either two of the following particular classes. So it will submit a bid to either a low demand class or a high demand class. So a high demand class already has an upper bound amount of elements attached to, already matched to it. So it's sort of, it cannot handle any more elements. Or it will submit a bid to a low demand class, which does not yet have this upper bound amount of data elements, so it can definitely take on a few more. So if it submits a bid to a low demand class, then it gets matched immediately to the class. Now, if it submits to a high demand class, then it still gets matched to the class, but the lowest bidder of the class thus far gets kicked out from the class. So basically, in this case, the number of elements get matched to this high demand class doesn't change. It's just they will kick out the lowest bidder. And then because this class is so popular, it will increase the price of the class. So eventually what will happen is that the high demand classes will increase their prices so much that eventually some data elements will switch their bid to a class that will offer a bigger bang for their buck. So some data elements will actually switch their bid once the prices get too high. Now, the upper bounds fit very nicely into this perspective, but unfortunately we can't handle lower bounds this way. So we need something else. So we will then have a reverse auction, which will take care of the lower bounds. Okay, so this is the pseudocode for the forward auction. So basically, if the class is already full, if it cannot handle any more elements or any more members, then you kick out the lowest bidder. And then if it doesn't, then you just add this. If it's a low demand class, then you just add the data set element to the class. Okay, so here's the second part, which is the reverse auction, which handles lower bounds. So it proceeds in the following way. So if a class is deficient in members, so basically it doesn't have the lower bound amount of members, what you do is you pick a data set element already matched to another class, but that was closest to choosing the deficient class by computing a certain optimization problem. Once you find this element X, you will transfer X to the deficient class. So you'll unmatch it from its current class, and then you match it to the deficient class. So then the deficient class gets one more element. Then you will update the incentives and prices. Now, if this class is still deficient, you keep going, you keep doing the same thing until it fills up. And then you keep doing this with each deficient class until each class has this lower bound amount of members. So here's the second part to our algorithm. It's the reverse auction. Here's the pseudocode for it. So here, if a certain class doesn't yet have the lower bound amount of members, what you do is you just find an element matched to another class, and then you move it to the deficient class. Okay, so our algorithm consists of a procedure using this forward and reverse auction. And to make the algorithm more efficient, we're actually going to use epsilon scaling, which I'll explain in a second. So our algorithm, what it will do is it'll compute a sequence of partitions of our data. And then sort of with each iteration, the partition will get more and more optimal. So to obtain the partition of the next iteration, what you do is you set the epsilon to be some initial value, and then you recompute your auction coefficients using the previous or the partition that you currently have. So you recompute the auction coefficients, you set the epsilon, and remember the epsilon was the parameter in the bid value that is there to make sure the algorithm does not run into an infinite loop. So once you set those things, you will alternate between running the forward and reverse auction while decreasing the value of epsilon each time. So this is called epsilon scaling. And once the epsilon value is small enough, then you end, and then that will give you a partition, and you just keep going with the next iteration. So once epsilon is small enough, you can then get your partition of the data. And then, so this epsilon scaling exists to make the algorithm quicker or run more efficiently. Yeah, so this is the pseudocode for our algorithm. So here we will compute the auction coefficients, and then we will alternate between running the forward and reverse auction while decreasing the epsilon after the reverse auction. And then we'll do this some number of iterations. So we'll kind of compute the auction coefficients, and then do this epsilon scaling, and then we'll do everything for a certain number of iterations. Okay, so just a little bit about the time complexity. So it turns out that the complexity of both the forward auction and then the reverse auction using epsilon scaling, so it appears to grow like the following. So here, C is a value determined by the auction coefficients, N is the number of data elements, and then M is the number of classes. And then we also have another constant. So using epsilon scaling will speed up the procedure a little bit. Okay, so then I'll say a little bit about the application. So the application in this method is to 3D sensory data. So classification of 3D point clouds is an important problem with applications such as autonomous mapping and navigation. So point clouds actually arise through laser-based imaging, and they represent 3D objects and scenes. Now, point cloud classification is a very challenging task due to many reasons, such as I mentioned before, so lack of adequate high quality training data or labeled data. Sometimes you can have overlapping objects, and you could also have noise in your data. So it's a very challenging task, and we're going to apply our procedure to this data. And as I mentioned before, we're not going to use a lot of labeled data. So we're going to use at most 2.5% of the data as labeled. And for a couple data sets, we'll use, I think, half a percent of the data will be labeled. Okay, so we're going to use the following data sets. So the Oakland 3D point cloud data sets, Ankeny point cloud data set, and the buildings point cloud data set. And they each have quite a bit of points. And one thing I'd like to mention here is that for these kinds of data sets, basically each point has at most maybe 6 coordinates, like the geometrical value and also maybe some color information. So it's a very small feature vector for each data set point, which makes it easy computationally, obviously. Okay. So for 3D point cloud classification, we're going to construct region homogeneity terms using a combination of a few different things. So we're going to use the correlation matrix, we're going to use point coordinates, normal vectors, and variation of normal vectors. Okay, so we're going to use at most 2.5% of the points as labeled, and for some we use less than 0.5% of the points as labeled. So the method is quite fast, so it only takes a few minutes for these data sets, including graph computation. And one property that allows it to work fast is because each feature vector is quite small. So as I said before, each feature vector only has a few values in it. Okay, so let's take a look at some results. So this is the first data set. So Oakland 3D data set of the CMU campus. And this data set has a few different scenes of the campus. So these are 4 of the scenes. And in these scenes, the goal was to classify the data into 3 classes. So the building, the vegetation, and the road. So the road is in brown, the vegetation is in green, and the building is in blue. So here are 4 of the scenes of the data set. And over all of the scenes in the data set, we got an accuracy of 97.91. And let me give you an example of a few other scenes. So here's a few other scenes of the CMU campus. For most of them, we classified into 3 classes, so ground, vegetation, and building. But for example, for this scene, we actually also had a 4th class. So the 4th class are the poles, which are in red. So the last one is a 4-class classification problem. Okay, so the next data set is the Ankeny data set. So this one we classified into 4 classes. So building, road, trees and also low-lying vegetation or grass. So this is a 4-class classification problem. So we also obtained a high accuracy for this data set. And then for the last one, which is the buildings data set, here we also classified into 4 classes. So building, trees, grass, and road. So overall, we have derived modified auction dynamics technique for data classification and segmentation. So just to summarize, some of the advantages of the method include the fact that it works well with data with limited labeled samples. So oftentimes you don't need that much labeled data for this method to work, which is great because unfortunately for a lot of applications, labeled data is very scarce. And a lot of the methods do need quite a bit of labeled data. It is also unconditionally stable with respect to the parameters, and it is able to incorporate class size information in the form of upper and lower class bound or class size bounds. So for each class, you can incorporate the lower bound and the upper bound for the class size. And overall, we did find that it is often quite accurate in during the experiments. So yeah, thank you so much for coming to my talk.
Okay, thank you very much, Ekaterina. Right, I'll stop the recording and then we can ask questions.
Thank you.